Hello and welcome back. Today we have this really cool log trig integral. We have the integral from 0 to pi by 2 of log 1 plus sine x times log 1 minus sine x dx. Now, one possible way of solving the integral could have been expanding either one of these log trig functions using these series expansions for either log 1 plus x or log 1 minus x, and then performing or solving the subsequent integrals and switching up operators and all that exotic kind of stuff. But I did not follow that approach. My approach was quite different, in fact. And it made heavy use of symmetry as well as the properties of the logarithm, as in repeated application of those properties. And in fact, these symmetries were quite beautiful. I quite enjoyed the solution development, so let me show you exactly what I'm talking about. Funny thing, only now have I noticed that we're integrating an even function of x, because if we replace x by negative x, then sine x turns into negative sine x, and by that token we have log 1 minus sine x times log 1 plus sine x. So we're integrating an even function of x, and we might as well restate the problem to be an integral from negative to positive pi by 2. And then we can write this as twice the integral from 0 to pi by 2 of log 1 plus sine x, wait, terribly sorry about that, 1 plus sine x times the logarithm of 1 minus sine x dx. But what on earth are we going to do with this product of logarithms? I mean, sums of logs are quite nice to deal with, and so are differences of logs, but here we have a product. Well, recall that twice a product, that is 2ab, equals a plus b whole squared minus a squared plus b squared. So if we call a log 1 plus sine x, and we call b log 1 minus sine x, then in fact we have 2 log 1 plus sine x times log 1 minus sine x equal to log 1 plus sine x plus log 1 minus sine x, whole thing squared, minus log square 1 plus sine x plus log square 1 minus sine x. Now, again, you have a sum of logs over here, so we can write it as the log of a product. So we have log 1 minus sine square x, because 1 plus sine x times 1 minus sine x is, of course, 1 minus sine square x. And this thing is, of course, equal to cosine square x, and we're squaring this thing. But wait a minute, this could be written as twice the logarithm of cosine x using the properties of the logarithm, and taking the square gives us 4 times log square cosine x, and we have minus log square, 1 plus sine x minus log square 1 minus sine x, and this implies that the target integral I is actually equal to, well, we need 3 different integrals to solve it. We need 4 times the integral from 0 to pi by 2 of log square cosine x dx, which I shall call I sub 1, and minus the integral from 0 to pi by 2 of log square 1 plus sine x plus log square 1 minus sine x. So instead of dealing with 3 integrals, I'm actually just clubbing up the other 2 together and solving it as a single integral I'm going to call I sub 2. And the main reason for that is, well, these 2 integrals are actually very closely related. And again, symmetry will have a big part to play. So we're just going to solve it as one nice big integral. And the first thing I'd like to do is perform the transformation going from the x realm to the pi by 2 minus x realm. So we have a phase shift by pi by 2, giving us the integral from 0 to pi by 2 of log square 1 plus sine of pi by 2 minus x is, of course, cosine x. So we have log 1 plus cosine x plus log square 1 minus cosine x dx. And now we can make use of the double angle formula for the cosine function. We know that cosine 2 theta plus 1 equals 2 cosine square theta, and cosine 2 theta no wait, 1 minus cosine 2 theta, that is, equals 2 sine square theta. And this means that the integral I sub 2 is in fact the integral from 0 to pi by 2 of log 2 cosine square x by 2 whole thing squared plus log 2 sine square x by 2, again, whole thing squared, integration with respect to x. So now using the properties of the logarithm, we can expand the log of a product as the sum of logarithms, but remember, we're dealing with squares here. So what we have here is in fact log 2 plus log cosine square x by 2, which is of course twice the logarithm of cosine x by 2, so that's quite nice. And this means that I sub 2 equals the integral from 0 to pi by 2 of log square 2 plus 4 log square cosine x by 2 plus 2 times, no wait, it's going to be 4 times log 2 log cosine x by 2. Terribly sorry about that, much better. And then we have a lot of other stuff. We in fact need another log square 2, then we need 4 log square sine of x by 2 plus 4 log 2 sine x by 2 integration with respect to x. Now let's try clubbing up some like terms. So we have twice the integral from 0 to pi by 2 of log square 2 dx, which is of course going to be equal to log square 2 times the length of the interval, which is pi by 2. We have some nice cancellation taking place. In other words, finally we have pi times log square 2. Then we have 4 times the integral from 0 to pi by 2 of log square cosine x by 2 plus log square sine x by 2. Then we have 4 times log 2 times what exactly? Let me just give myself a little bit more writing space. Oh, dear me. I did not want to take that 2 with me. And there we go. Laser precision, I would say. Anyway, we have 4 times log 2 times the integral from 0 to pi by 2 of what exactly? Well, we have log cosine x by 2 plus log sine x by 2, and absolutely no room to write the dx, but I omitted numerous times anyway, so it's cool. Let's deal with this integral first because it seems fairly simple. So let me just pick a different color to highlight it. Here we have the integral from 0 to pi by 2 of what exactly? Well, we can write this as log cosine x by 2 times sine x by 2 dx, meaning that we have 1/2 of sine x by the double angle formula. So we have integral 0 to pi by 2, 1/2 log 1/2 sine x dx. And again, properties of logarithm, integral 0 to pi by 2 log 1/2 plus the integral from 0 to pi by 2 of log sine x. And this is, of course, Euler's log trig integral, which equals negative pi by 2 log 2. And here log 2 is, of course, equal, log 1/2 is equal to negative log 2. And we also have the interval length being pi by 2. So that means this integral sorts out quite nicely to negative pi times log 2. So we just get rid of this bulky thing in favor of negative pi times log 2, and that gives us 4 pi log squared 2, and we already have pi log squared 2, and this implies that I sub 2 equals this integral that I probably should now call I sub 3, or why not m, or maximus decimus meridius. And so I sub 2 equals 4 times m minus 3 pi log squared 2. And now, what about the integral m? Well, this is a very interesting one. We have the integral from 0 to pi by 2 of log square cosine x by 2 plus log square sine x by 2 dx. And the first thing I'd like to do is let x by 2 equal u, which implies that dx equals 2 du, giving us m equal to the integral from 0 to pi by 4 now of log square cosine u plus log square sine u, 2 outside because of the differential element. And this is pretty cool, but now I need one more transformation, and that is actually the phase shift of letting u here equal to pi by 2 minus t. So that gives us m equal to the integral from where to where? Well, du is in fact negative dt, so we do have a negative sign outside. And for the lower limit, now we have pi by 2, and for the upper limit, pi by 2 minus pi by 4 is just pi by 4, and we have log square cosine pi by 2 minus t is of course sine t, so we have log square sine t, and plus sign here, log square cosine t, integration with respect to t, and of course by switching up the limits, we are rid of the extra negative sign outside. So we have the integral from pi by 4 to pi by 2, and this is actually very, very nice, because we now have two versions of the integral m, and this implies that 2m equals twice the integral from 0 to pi by 4 plus the integral from pi by 4 to pi by 2 of all of that stuff. And the 2's of course cancel out quite nicely, and the integrals combine together to give us the integral from 0 to pi by 2 of log square sine t dt plus the integral from 0 to pi by 2 of log square cosine t dt. And a phase shift for this integral, terribly sorry about that, from the t realm to the pi by 2 minus t realm will of course give us log square cosine t in both cases, which implies that m here is just twice the integral from 0 to pi by 2 of log square cosine t dt. So I sub 2 is actually equal to 8 times the integral from 0 to pi by 2 of log square cosine x dx, where I've just renamed the dummy variable from t to x. And we also have this negative 3 pi log square 2. And what about the target integral I? Well, that was equal to 4 times the integral from 0 to pi by 2 of log square cosine x dx minus the integral I sub 2. And this implies that I here is now negative 4 times the integral from 0 to pi by 2, terribly sorry about that, of log square cosine x dx plus sine 3 pi log square 2. Okay, cool. So we only have one final target, and that is this integral. Now this integral deserves a video of its own. If only there were such a video solving this integral. If only such a video existed in which exotic functions like the beta function, the gamma function, the digamma function, and dare I say it, the trigamma function, all come together, bound by a sophisticated technique like Feynman's trick of differentiating under the integral sign, all employed to solve this beast of an integral. If only such a video existed where the author would describe such techniques and explain the solution development with such simplicity that even a beginner could understand it and appreciate the beauty of the mathematics involved. Alas, if only such a video existed. Oh wait, in fact such a video does exist. I myself solved this integral quite a while back, and it sorts out to pi by 2 times log square 2 plus pi cubed by 24. So we multiply that by negative 4, giving us negative 2 pi, terribly sorry about that, log square 2 plus, minus sign pi cubed by 6 plus 3 pi log square 2. And this implies that the target integral I equals quite nicely pi times log square 2 minus pi cubed by 6. Which is a beautiful result indeed, so beautiful that I forgot how to pronounce such basic words. I hope you enjoyed the video. Be sure to like and subscribe. More importantly, I hope you learned something from the video. Share the video to help promote the channel, and do drop me a follow on Instagram as well. And in case you like the effort I'm putting into my work, consider supporting me on Patreon. All links are in the description box. Don't forget to check out that video on, log squared cosine x. This integral was an absolute banger. Thank you. See you next time.